Hello, good afternoon, or at least it is afternoon right now. I'm Rafael Maciel, and I'm here to make a presentation about our work, which is entitled A Comparative Numerical Analysis of the Available Power Between Regular and Irregular Waves, a case study of an oscillating water column converter in the coast of Rio Grande, Brazil. So to start, I would like to talk a little bit about energy, which is a fundamental element in our everyday life. So when we talk about energy and electricity, the source of that energy matters. And a lot of the sources that we have nowadays are non-renewable, which means they cannot be rapidly replaced by natural means at a fast enough pace to keep up with consumption. So, in a report by the Intergovernmental Panel on Climate Changes, we have the sources in the global energy supply, and renewable energy only accounts for 12.9% of that total. And then we have in the renewable energy section different sources. Ocean energy, which is the focus of our study, is only responsible for 0.002%. And in Brazil, that number is probably lower. In contrast, the annual mean wave power in the Brazilian coast, especially in the south and northeast region, is quite high, as shown by Espindola and Araújo. So the aim of this work is to compare the hydropneumatic power available in an oscillating water column type converter device installed on the coast of Rio Grande in the state of Rio Grande do Sul in the south of Brazil, subjected to irregular waves of a realistic sea state and to regular waves representative of this sea state. Before we continue, I would like to talk a little bit about the operating principle of an oscillating water column device. So basically, the device has three main parts, which is the hydropneumatic chamber, which is the part that is inserted in the water. There is a turbine duct, and inside the turbine duct there is a turbine. So the level of water goes up and down, and that movement comprises the air inside the chamber. That movement, that compression of air, makes the turbine spin, which then can generate electricity. So for the simulations in this study, we use two models. The first one is called Tomahawk, which is a spectral wave model that simulates sea states for a certain space for a certain time. In this study, we considered the continental shelf and the coastal region of the state of Rio Grande do Sul, and the time was the year of 2014. So from the triangular element mesh, we took the point corresponding to the node 1545, which is a point 2 kilometers away from coast and 9.62 meters deep. So to simulate the sea state with Tomahawk, we used three types of boundary conditions. The first one was responsible for the wave parameters. We used then the wave wash 3 wave model from the National Oceanic and Atmospheric Administration, NOAA. For the surface wind boundary condition, we used historical data from the Reanalysis 1 project, also from NOAA. For the bathymetric data, we used nautical charts from the Directorate of Hydrography and Navigation of the Brazilian Navy and the General Bathymetric Chart of the Oceans. So from the sea state simulated by Tomahawk, we were able to obtain the significant height and average period for all the year 2014. So the most frequent significant height for that year was 0.66 meters, and the most frequent average period was 6.3 seconds. That corresponded to a 6% from total and happened a total amount of 2,000 times. Here we have a time series of significant height and average period for all the year 2014. The color band in each graph is the part that is most frequent as shown in the bivariate histogram. Then we took the daily variance spectrum for each day of the year And then we chose the spectrum that had a significant height of 0.66 meters and an average period closest to 6.3 seconds, which in this case was 6.32. That was August 23rd, 2014, and it had a peak period of 9.65 seconds. The second model we used in the study was a fluid dynamics model, in this case ANSYS Fluent. It is marketed by ANSYS Incorporated. It has a formulation based on the finite volume method. It solves the momentum and continuity equations, and it uses the volume of fluid method to simulate and track the multiphase interface, in this case the interface between water and air. So the coupling between Tomahawk and Fluent occurs through wave velocities, which are obtained from Tomahawk and used as prescribed velocity boundary conditions in Fluent for the generation of irregular waves. For this, it was necessary to use the SpectWave software, which reads the C-States database generated by Tomahawk, converting its spectral data into time series of surface elevation and orbital wave velocities using inverse Fourier transforms. So the second computational domain that we had was the numerical wave flume, where we simulated the waves obtained by the first model. So on the left we have the red dashed line, where we use the prescribed velocity boundary condition, also called here velocity inlet. The green dashed line is the boundary condition for atmospheric pressure. The solid black line on the bottom and on the right side are walls. And on the right side of the flume we have a numerical beach, which is a portion of the flume that damps the instant waves, so they cannot reflect back. And later on, the device, the oscillating water column device, will be inserted. In order to define a spatial and temporal discretization of the wave channel that allow the proper generation of irregular waves, mesh convergence and time-step tests were performed. For each test, 5 minutes of propagation of irregular waves were simulated, and 3 parameters were analyzed: the number of division in the wave maker, which is called here delta V, the time-step size, which is called here delta T, and the area of each mesh element, which is called here delta A. So for the wave maker spatial discretization, 18 simulations were performed. The increase in precision when using 25 elements in the wavemaker in comparison to 15 elements did not result in an increase in simulation time. In contrast, the increase from 25 to 50 elements resulted in a large increase in simulation time, but in small significant difference in results. Therefore, 25 divisions was adopted for the wavemaker spatial discretization. Next, the spatial and temporal discretization of the wave flume were defined. This table shows that from delta A equals to 0.8 squared meters to 0.5 squared meters, there was a 10.28% decrease in the calculated root mean square error, which represented a considerable improvement. From 0.5 to 0.2 squared meters, there was a reduction of only 4.55%, and for 0.1 squared meters, 2.05%. For the time step, it's the same idea. From 0.07 seconds to 0.05 seconds, there was a decrease in 1.23% in the root mean square error, and from 0.05 to 0.3%, there was a decrease in 1.02%. Ideally, the chosen configuration would be the most refined, however, there is the computational effort issue. Next, we inserted the oscillating water column device and the mesh. The dimensions for the device were the same as those found in the Pico device in Portugal. So after the device was inserted in the mesh, we had a refinement increase in the region before and after the device. We then put some numerical monitors in the wave flume to monitor the surface elevation, which in this case are monitors A and B. The C was responsible for the static pressure, and D was responsible for the mass airflow. In Fluent, 3 simulations were performed. The first with the imposition of irregular waves generated from velocity profiles. The 2 others with regular waves representative of the sea state for the year 2014. Here we have the surface elevation at the entrance of the wave flume. The blue line represents the elevation obtained through the conversion of the spectrum obtained from Tomahawk, and the red line corresponds to the surface elevation simulated by Fluent. It is possible to notice that the waves represented by Fluent have a slightly lower peak than the ones from Tomahawk. The root mean square error for this simulation was 0.12. Here we have the surface elevation at the entrance of the wave flume, but now with regular waves. On the top we have regular waves using the peak period, and on the bottom using the average period. The root mean square error for the simulation using the peak period was 0.08 and for the average period 0.04. Here we have the same simulation but now with different monitors. We have the surface elevation at the entrance of the wave flume, which is the one in red, and the surface elevation at the center of the device, which is the one in red. Finally, an analogous analysis was performed. Since irregular waves propagate at random, it became very difficult to make a comparison between surface elevation at the entrance of the wave flume and inside the device. Therefore, the simulated sea state variance spectrum is presented. It can be seen that the spectrum at the entrance, which is the red line, is quite similar to the original spectrum, with the exception of some noise level introduced, possibly due to the non-linearity of the fluid dynamics simulation. However, 109 meters from the beginning of the wave flume, inside the device chamber, which is the green line, there is an evident loss of energy in relation to the channel entrance, especially at higher wave frequencies, which indicates that only waves of lesser frequency are propagated without loss. This loss occurs in part due to the wave propagation by Fluent itself, and in part due to the fact that short-period waves are reflected by the device wall and have no effect on the surface elevation inside the device, thus explaining the loss and the apparent variance spectrum smoothing observed. Here we have the instantaneous hydropneumatic power available in the turbine duct of the device. For irregular waves, a power of 5.12 watts was obtained. For the representative regular wave with peak period, 4.07 was obtained, while for the representative regular wave with the mean period, 14.17 watts was obtained. The difference between the use of the mean period and the peak period is due to the fact that mean period is, in this case, 3.5 seconds less than the peak period, causing the wave propagation velocity and consequently the free surface vertical velocity to be greater for regular wave with the mean period. So, from this work, we can conclude that the hydropneumatic power obtained using regular waves showed a value of around 0.78 times the hydropneumatic power obtained from regular waves generated from the peak period. For regular waves generated from the mean period, the hydropneumatic power presented a value 2.73 times greater than obtained with irregular waves. When using regular waves to represent a sea state to estimate the hydropneumatic power of an oscillating water column device, peak period provides, on average, a better estimate than mean period. Finally, when performing a simulation of hydropneumatic power available in an oscillating water column device, using regular waves, the period of these waves will directly impact the available power. Thank you.